Well, welcome back and welcome to week 4. Today's topic is volumes. We're not talking about simulation volumes here, so we're not talking about smoke, fire, explosions and particles and stuff like that. That's next week. This week we need to get a really good handle on how Bifrost does volumes, how Bifrost handles volumes, and the different kind of volumes there are. So we'll start with that. Create a graph. There's your basic everyday Bifrost graph. I don't need those guys. I'm going to make a sphere. Like that. Let's give it a little bit of radius so we can see what we're doing. And here's the first node you're going to need for volumes. And I'm going to use this to explain what they are and how they work. So what you're going to need is mesh to volume. Like so. And what this will do, it will take your incoming mesh, which in our case is just a sphere. We could use anything we like. And so this is literally converted this to a volume. So let's have a look at it. Threw down a terminal, and that is the default volume. So this is what's called a fog volume. There are two kinds. This is a fog volume because I've told it to store fog density. And literally what this is doing is filling this object with fog. So let's take a step back and talk about what the basics of volumes are. When I say the basics, what I'm talking about is the basic unit volume. When you're making a mesh, the basic unit of a mesh is a point and an edge and a face. Those are the three things that make up a mesh. Yeah, when you're making some sort of cool visual effect, usually the basic unit of visual effects is particles, but don't quote me on that. Points in space. We're talking about the most basic thing that makes up an object. So if we were just to look at our sphere, go to wireframe mode, you can see that the sphere is made up of edges, points, and faces. And together, they all make a sphere. Just plug the volume back in. What volumes are made out of are voxels. And what they can be thought of really literally as 3D pixels. So let me show you that. Let's plug in a volume scope in here and then plug that into our output. And suddenly all of these weird squares turn up. If we go out in 3D, you can see that they're actually cubes. What these are representing, what these are showing you are the voxels in your volume. Now I hear you say, when we look at the volume, it doesn't fill up anywhere near that as much space as the voxels do. And that's because when we look at the volume scope here, what we're looking at are the tiles that make up the volume. And inside of each one of these tiles is 4 by 4 by 4 voxels, which, if you do the math, is 64 voxels. Just like pixels in a 2D image, pixels being the basic unit of a 2D image, voxels are the basic unit of a volume, and they're 3D. And they can carry information. Things like position and velocity and sign distance and fog density. And what we're seeing here with our volume is our fog density. This is quite literally how dense is the fog inside each voxel. This is pretty useful for when you're doing things like clouds and smoke and stuff like that. We'll be doing a little bit of that today. The other one that we have is a level set. And when you're storing a level set, what you're literally doing is storing the distance to each point on that sphere. If I come in here, you can see that it's hollow and empty. We can take a look at our tile tree. And again, you can see that the tiles extend out into space, even though it doesn't look like there's any voxels in there. If I wanted to say, show you the fog density, really all I'd have to do is turn this off, turn this guy back to fog density, and you can literally see it. I can change that density so it becomes less and less dense as I slide this, or more and more dense as I slide this. So it is literally how dense is the fog contained within the voxels of the volume. But when I go to store level set, it just looks like a kind of rough version of the sphere. You can see some lines in it and stuff like that. And that's because of the resolution. You see here in your volume parameters, you have a resolution. The first thing we need to talk about is the resolution mode. So, and this applies to both kinds of volumes. So when this is set to relative, the voxel size, let's just pop this back on. The voxel size is relative to the bounding box of the input mesh. So if I was to say, take this and scale it up to 10, my tiles have got bigger and consequently so have my voxels. Go back to 5 and you can see what I'm talking about. But if I've got this set to absolute, you see a big change there. That means the voxel size is in world space units. So that means each voxel in the detail size is 0.05 world space units. And when I change the scale of this back up to 10, It doesn't affect the voxel size at all. It is a little slower though. There's our fog density volume, and you can see the tiles here. If I go to the volume and switch this over to relative, you can see that these tiles are now relative to the size of my object. So that applies to both kinds of volumes. We're going to talk about level sets in just a minute, because level sets are super handy things. Let's set this to absolute, so we've got a nice high res, and we'll just switch it over to level set. Now you notice I can turn both of these on. So I can carry the level set information and the fog density information at the same time, which when you go down the road and you're building things using volumes, so if you model using volumes, you can make all kinds of stuff using volumes. It's good to be able to carry both of them out. We're just going to be working with the level set for now. So yeah, the level set is storing the signed distance of every voxel. So let's have another way to look at that. And you remember we've done some work on fields, and we can convert volumes to fields by making a voxel field. So this will convert a volume's voxels into a field for us. And it's just a good way to show you. Now this is already set up to be a voxel sign distance, so this will get us a look at the distance field that the level set is showing us. All I have to do is do a scalar field scope. Pop that in there. Let's use our sphere as our bounds geometry, like so. And let's plug this in to where the volume scope was for just a second. As always, you need to do a little bit of adjustment to get things looking right, but you can already see what's kind of going on. You've got field values all the way out here to the bounds, and then you've got nothing in here. So let's just adjust this really, really quickly. So we'll make the point size a lot smaller. We will change our size remap so it remaps from -1 to 1. So now we've got points in the middle. And we'll just really quickly go and change some colors so that things look a bit better. So if I zoom in here, what you can see is I've got lots and lots of white points out here and black points out here and here. And what this is telling me is that outside of the volume, let's just turn on the sphere for now. And we'll go to wireframe. So what you're basically seeing is the distance to the surface of that sphere. It'll look a little better in 3D. And you can see that towards the center, the points get darker and smaller, which means that inside here, if I go to wireframe mode, these values are negative as they get further and further away from the surface of the sphere. Inside the sphere, they're negative. Outside, they're positive. Sign distance and level sets are awesome. Enable you to do all kinds of very cool stuff. They allow you to do things like really, really quickly checking if one object is inside another one. Because if you sample the position of a voxel sign distance, if it's negative, it's inside. If it's positive, it's outside. It's very, very easy to work with. So that's basically the two kinds of volumes. So if we come over here and do this again, and we'll just turn off our scope for a second. So there's our fog volume, where each voxel contains a density of fog. Well, here is our level set volume, where the voxels store the set of points with the same sign distance value. So basically the sign distance of each voxel is stored in a level set volume. Refer to the PowerPoint for a deeper dive on this, but this is basically what you need to take away from this is that there are two kinds of volumes. One is foggy, the other one tells you the distance to stuff. That's the simplest way to think about it. Okay, let's go on and make something with them. So following along with the PowerPoint, I'm now up to slide 9, as you should be too. Maybe I should play a little sound when it's time for you to change the slide, kind of like those storybooks. Anyway, moving right along, let's do something with sign distance fields. What I've got here is a couple of mushrooms. Let's drag them into Bifrost. This is what happens when you bring in two things. It inputs by the path in Maya, which lives up here, so you can change that. And spits out an array. So the first thing we're going to need to do is merge that geometry. Merge geometry. And let's do that thing that I showed you guys for troubleshooting, where we just take a terminal. And we're going to move it along with us as we go. So let's have a look at our lovely merged mushrooms. There we go. That is most definitely a mushroom. Next thing we're going to need to do is, let's put that up there, and mesh to volume. Now we've obviously got a foggy mushroom. We don't want a foggy mushroom. We pretty much want a sign distance field mushroom. So that's just a matter of switching this to this. Now we don't have a foggy mushroom anymore. So from here, what we're going to do is make ourselves a little voxel field. And this is where we say goodbye to our terminal because we can't show fields in a terminal. So voxel field. And like I showed you just before when we were doing all that sign distance stuff, what this does is it converts a volume to a field with the values from that volume inside the field. So basically you need to tell it which property you're getting, and it's going to convert it to a field based on that property. So voxel sign distance, because it's just a distance to the edge of the object, whether inside or outside, that's a scalar field. So we'll just go in here and make that a scalar field just to be safe. And let's see if we can get something going on with a look. We'll see if we can take a look at it by using a scalar field scope. We might just be able to use our terminal again. I'm probably going to make this a bit smaller. Let's pop this out and see what we get. That was probably a little too small. So now you can see we've got an inverted field of our mushroom, because what happens is the sign distance field is positive outside the object, which is why we're seeing all of this, and negative inside it, which is why we're seeing nothing. But you get the idea. You can see the blue mushroom in there. Well, that's the sign distance field of the level set that we're making in the volume. And then we're converting it to a field using the voxel field. So next we need to do a mask field. And what a mask field does is make our life easier. It's going to take everything that's negative and make it 0, and everything that's positive and make it 1. So it's like a super hard clamp. So it's a little hard to see. Let me just take the size down a wee bit so it's a bit easier to see. But basically what's happening now is it has cut out everything inside the mushroom and made everything outside of the mushroom the same value, which in this case is 1. So from here, what we're going to do, and I might give up trying to show fields because it's getting a bit difficult. We're going to multiply this field. And we're going to multiply this field by a fractal noise field. And because the mask field converts everything from whatever it is to 0 and 1, you can see here returns a field whose value is 1, where the input scalar field is positive, and 0 everywhere else. So it's kind of worth it for that. We're just going to use a bog standard fractal noise field, and I'm going to multiply this field by the fractal noise field. Let's pop that into this and see what we get. So you see we're starting to get randoms. Randoms all over the place, but not inside the mushroom. Just quickly increase that point size and increase the divisions as well, so you can kind of see what's going on here. There's still none of that field is happening inside the mushroom. There's a big empty hole here, and the reason for that is we're going to grab ourselves a sphere. A sphere? Yeah, let's do a sphere. We'll just up these a bit, just so it's got a bit more resolution to it, because what we're going to do now is displace it. So we're going to displace this sphere with this field, and now, hooray, hooray, we can go ahead and use our terminal again. I'm going to really quickly make a nice transparent shader so we can see what's going on, and feel free to copy this yourself. This is a handy thing to know how to do. I'm going to take the object, constant surface material, put that surface material into the surface material, the material definition into there. Let's just get this out to our terminal so you can see our mushroom there. It doesn't really have any kind of detail in it, which is okay, because all I want to do now is just give it a bit of transparency so I can see through it. And you can kind of see what's happening to the sphere now. So if I just translate this, I mean, the PowerPoint does it in Maya, and you're free to do that as well. Make a sphere, bring it in, move it around in Maya. It might just be a bit easier. but I'm okay to do it in Bifrost. In fact, if I really wanted to, I could just create a locator here, drag that in, put a transform points on my sphere, plug the locator into it, then plug that into the displace points. And now when I take my locator and move it, I can just move my Bifrost object around. So I'm going to put that over there. And the nice thing too is that if I scale my locator, it works as well. And you can kind of see what's happening here. There's a bit of an offset, but when it leaves the field that the mushroom is making, so the mask here that the mushroom is making, it's hitting this fractal noise field and starting to displace. Now there's a great big gap here in between the edge of the mushroom, which you can kind of see by the transparency, and where the displacement starts. And the reason for that is when we made our volume, we left our resolution mode at relative. So if I put a volume scope on this, just like that, and I plug that into my terminal, you can see that how big the tiles are, the tile boxes with our voxels in them are. That's because I've got my volume here set to relative mode. If I set that to absolute mode, you can see how much smaller the tile cubes get, and therefore how much smaller the voxels are. Let's just unplug that for now. And you can see now that that's a much closer match to the edge. And that's basically this exercise. Basically, what I'm trying to show you here is that we can use a field, which we have here. We can use a field to mask, or to displace an object. There's the object we're displacing. Here's the transform we're performing on it with the locator. And you can see that when our sphere is inside our mushroom object, it stays a sphere. But when it's outside, it runs into this field. This field is now displacing it because inside of our mushroom object, this field's displacement value is 0. And I can show you this by just grabbing the locator and I'm going to pull it out of there. So that's now fully in the field. Let's just hide our scope for a second. So that's what the sphere looks like. You can change its magnitude of displacement and all of that kind of good stuff like you can do on your fractal noise field. You can do all of that, but as soon as it goes inside that mushroom object, the displacement falls away to 0. You can see that there. So this is the concept of making a volume, using it to make a field, and then masking that field. And of course, you can reverse that as well. You just need to do something like, and remember that this data is 0 to 1. So if I take a scalar field of 1 and subtract this field from it, just works with the math nodes just like everything else, then this should reverse my mask field. And there you go. So now it's displacing inside the object, but not displacing outside of it. So very good for setups, all kinds of things you can do with this. Lava lamp anyone? And you can even see it's obeying the mushroom stalk here as well. It's displacing it as long as it's inside there. Or, as it were, outside. And of course, Bifrost being Bifrost, procedural, non-destructive, all that cool stuff I keep going on about. What I can do too is I can literally just put an if statement in here and we're able to switch it, because I like to do that. I like you guys to know how to do that and get used to doing it. So let's make sure I've got nothing selected and hit if. So basically what I'd want to do is if it's turned off, I just want the mask field, and if it's turned on, I want the mask field subtracted from 1. It goes into mask, and then I can just switch that over. Maybe I put my locator in a better position so you can see what's going on. So half in, half out. There you go. So yeah, that's that. I'm going to call this graph shrooms1. And I'm going to hide it because we are now done with this part of the lesson. And I'll hide my locator too. In fact, I'll put them in a group and call it Shroom01 group because it's nice to name your things. And that way you can remember it. So now I can close this Bifrost shape. There it is there if you want to open it again. And we'll go on to the next one. So we're going to do something really, really similar here, but we're going to do it with the mushrooms themselves. So let's get into that. Because it uses a lot of the same setup as the last one, I'm just going to copy that over and bring it. So let's reopen our shroom shape. Pretty much going to need all the way up to voxel field. So all of this stuff. Copy that, close that, create graph, paste that. You can check to see if it's worked by having our old friend the terminal. First thing that hasn't worked is that. Plug that in. Let's plug this in, make sure it's working. Yep, we've got some mushrooms. And do we have a volume? Do we have a sign distance field volume? Yes, indeed we do. So we're good. So we've made a voxel field again, and it's the same settings. It's the sign distance. We're going to make a fractal noise field too, just like we did before. And this time we're going to plug this into the mask field. So we're using whatever the fractal noise field generates as our mask, right? And then I'm going to multiply the voxel field. This is where it gets a little different. Before we were using our mushroom as a mask. Now I'm going to use the noise as a mask. We're going to multiply a voxel field by our mask field, which gives us an area that is masked and an area that is not. And then I'm going to get it back the other way, field to volume. So if I plug the field in here, bring my terminal, let's have a look at that field. It would probably help if we change the field interpretation to sign distance and make sure we've got level set turned on. That's a bit better. So it's quite a low resolution. Let's set that to absolute so we can see what's going on. There we go. And you can see here that we have our mushroom with a whole bunch of holes carved into it. And we can change that by changing the frequency here. It takes a minute to work itself out, but you can see it's basically using the field to carve holes in our mushroom. So once we've got that far, let's make it a mesh. Volume to mesh, it's all the reverse of what we did to start with. So volume to mesh here and plug that in. What I'm going to do just to make things a bit faster is I'm going to take that back to relative, but I'm going to make it very, very, very small. So it's faster to calculate and you get an idea, but it's not the best of times, not the worst of times. And this is a good tip for working with volumes. When you're working with volumes, approximate at low res, do it so it's quick, and then up the resolution to see if what you thought is going to work. Most of the time it does. So we've got a volume to mesh now. Let's plug that in, and you can see that it's made us a mesh of that volume, which is great. And we can do all of the cool mesh stuff to it that we like to do, or that I like to do anyway. And this is explained in far more detail in the PowerPoint, but we're going to go from here. Just make sure that your input field is sign distance field and that you've got store level set on, because that's what we want. Then I'm just going to make this, I have a feeling that there's only one thing in there, so let's just get the first in array, just so that we're not dealing with arrays. It's going to be the same object. And let's just assign a material to it. Just so, we can look at it and it looks happy and stuff. So I'm going to do a standard surface material. I'm going to make that color somewhere in the light blue, like the PowerPoint did. Pop it in there. There we go. We've got a nice light blue mushroom with holes in it. Now the point of the exercise is I want to fill in those holes, right? I want to fill in those holes with the rest of the mushroom. So how on earth am I going to do that one? Well, that's pretty easy, really. All I have to do is invert this field and then make another mask. So if I can use negate, I think, on a field. Yes, I can, which will invert it. You can also multiply it by -1, a scalar field of -1. And then again, it's our mask field like we had before. Mask field there, and we're going to multiply our voxel field again. So we're just doing what's happening up here, down here, but because we've reversed it, we're doing it to the other parts of the mushroom. So if I multiply that, which is all good, that goes in there, and then it's just field to volume, volume to mesh, first an array, boom, boom. I can just copy that and paste it, I think. Goes in there, and what I'm going to do before I do anything else is just change the color. I'm going to get a nice sort of orangey red going on here, something like that, maybe, sort of a golden color. And then let's put this out. And there you go. You can see that it's filled in the mushroom. And because it's all controlled by the one field, if I say pop this frequency up to 0.33, you'll get this with your kind of peeling paint look. Your volume to mesh settings will be very effective on how these things look. So what I can of course do too is start making single values that apply to both things. So if I go to say volume to mesh on the blue one, the top one, there's my detail size, there's my smoothing, so I can change all of that to get a different look there. I can also go to field to volume here and make sure that I've got the same detail size here. So if I change that to 0.01, one of my volumes will get a lot coarser. So it's always good to do something like create a value node. Sometimes it flies off into the ether and you have to go and find it and plug it into both of these. So that means that if I now go like, I want a really coarse resolution or quite a fine one, I can do that. And also if I say take this to 0.05 and take my resolution mode, create a value node there, because just because it's a menu doesn't mean it can't be made into a value node. And we just go to resolution mode here. And so now I can go, okay, well, go absolute for me. So basically you're using a single field as a mask, and then you're using the inverse of that field as a mask on two different streams. But you've started with a field and literally you're making field to volume both sides. And now you've got this, which is kind of two halves of the same mushroom in a noisy way. That's just to get you going on sign distance fields. That's a good thing to do, because we're going to go ahead and maybe do a little bit of a practical use for it now. Also, you can see the lines here. These come from the original mushroom. So if I show these, yeah, so there's one of the lines in the mushroom. And this is a situation where my very high resolution is not doing me any favors. I'd want to smooth the volume or smooth the mesh anyway. But there are lots and lots and lots of things to do that with. Like we have compounds that'll do that. But this is the basics of working with SDFs. So there you go. Composite mushroom based on noise.